I would like to work for you a fluid friction problem, and you've already gone through this process and the calculus associated with it, but it comes up a lot in nature and in AP Physics in particular. So let's consider fluid friction. In this case, the fluid is going to be air. We're going to find the acceleration, velocity, and position for a slow snowflake. And if it's slow, there tends to be less turbulence, and as such, as a first-order approximation, the frictional force is related directly to the speed. So let's assume that's the case and consider the snowflake. And with that orchestral introduction, this should be quite an awesome problem. Let's do a free body. We got the weight, and we have friction, which is kV as defined. Now, the acceleration during the small interval of time during which it's speeding up after the snowflake is released, even though you just saw it moving at terminal velocity, but the point is, before it gets to that terminal velocity, it's accelerating. So the sum of the forces is unbalanced and acting downward. So the sum of the forces in the y is mg minus kv. So that's ma as always. Let's set this up as a differential equation. Realizing that a is dv dt. So we'll rewrite it. m dv dt is mg minus k. And then at terminal velocity, the acceleration is 0. And so let's set the left-hand side equal to 0. And we solve for mg, and we get kVt at that condition. So v terminal is mg over k. Now we'll take this original expression here in differential form, and we'll divide through by k in this equation. And we get m over k dv dt is mg over k minus v. But you'll notice that mg over k is actually what we had for v terminal. So this is that particular constant value of velocity, v terminal. So we have v terminal minus v. Now, m over k dv dt is v terminal minus v, which we know what to do with this. We have to bring the variables over to one side. So bring all the velocity stuff over to the left-hand side. dv over vt minus v. Multiply through by dt, bring it to the right-hand side, is k over m dt. So we also brought the constants k and m over. When t is equal to 0, at time t is equal to 0, v also is 0. So now we're going to integrate and multiply by -1 to put this in a better form, because you'll notice that we have a minus v here, and I'd like to get that as positive. So we're going to integrate from 0 to v of 1 over v minus vt dv is minus k over m integral of from 0 to t dt. So the integral of 1 over v minus vt is the natural log, and that's equal to minus k over mt. So we get natural log of v minus vt minus natural log of minus vt, when we stick 0 in for v, is minus k over mt. And we're well on our way. So finally, manipulating this, natural log of v minus vt over minus vt equals minus k over mt. And of course now we just need to e the expression. Oh. So we have vt minus v over vt equals e to the minus k over mt. So can work this out to 1 minus v over vt is equal to e to the minus k over mt, or v over vt equals 1 minus e to the minus k over mt. And so we're looking to solve for velocity. there it is, the velocity. So we have the velocity. Now let's get the acceleration. We had that the differential equation m over k dv dt is vt minus v. Now, it's not enough to simply say that, well, I know what the acceleration is dv dt, so we can solve for that and get k over m vt minus v. That's true, but it doesn't tell us how a is dependent on t. It just expresses how it depends on the velocity. And it does depend on the velocity, which is what makes it a harder problem. So, let's find out how it depends on t, not on v. So a is dv dt, which is the derivative of what we already solved, which is the velocity. So this is pretty easy for us. We bring the minus t out, and then the minus k over m comes down. E to the minus k over mt. vtk over m, e to the minus k over mt. At t is equal to 0, we have a is equal to the initial acceleration of gravity, because there's no fluid friction yet at no velocity. And so the acceleration is vtk over m. So the terminal velocity is mg over k. Thus we have that the acceleration, which we've already solved, is this expression here. When you put v terminal as mg over k, stick that in for this, it makes the m go away and it makes the k go away. The m and the k here. And we have a is g e to the minus k over mt. Kind of makes sense because this is the maximum value, diminished in time with this exponential. Finally, let's solve for position. This is not going to be a very simple equation. The position of the snowflake is not so trivial. Well, but we are adequately prepared to deal with this. We just know that position is integral of velocity. We've already solved for the velocity, so there it is. So as we integrate vt, we add a t to it. When we integrate this, the minus k over m comes down underneath, so that's multiplied by m over k. So there we go, from 0 to t. So let's plug in t for t, and we get this result. And subtract off plugging in 0 for t, and we get this result. Very good. So vt times t plus the vtm over k factors out, so we have 1, and e to the minus k over mt. And finally, our coveted result, there it is. Y is equal to vt times the quantity, t minus that expression, which includes the exponentials with t in it. So notice it's got a fairly non-trivial dependence on time. Namely, the position is a little bit complicated. It's a wonderful, beautiful expression of physics. Let's now graph the results of all this analysis. So we have the acceleration. Usually that's the simplest graph. The acceleration, of course, is not uniform. It is starting at g and ends up going down to 0. So it looks something like this. So there's the initial value, g, exponentially decreasing to 0. So there's implications that this has for the velocity. And we know the velocity is increasing, and it starts at 0 and increases to the point where it reaches a constant value. There it looks like that. And that constant value, of course, is v terminal. Now, if we take the slope of the line at the beginning, the slope of the line, of course, is the acceleration, and the acceleration at the beginning is g. What about the position? Fairly complex formula, but one thing we do know is that since the velocity is increasing, that means the position is increasing as well. Or you could also say, since the acceleration is positive everywhere, the position is increasing. And it's increasing non-uniformly. And it's curvy uppy rather than curvy downy. So, yet at the end, when the velocity or the acceleration is 0 and the velocity is constant, that means at the end of the interval, the position that we show here, we have a uniformly increasing position. So it's hard to express that qualitatively here, but there it is, something like that. And that is a nice summary of this motion.